Welcome back to Mechanical Engineering Made Simple.
Thanks for having me back.
So I want you to imagine just for a moment that you are the lead engineer on this massive multi-billion unit manufacturing facility.
Oh, that sounds stressful already.
Right. But you have the best CAD models in the world. The material science is just flawless. The structural math is absolutely airtight.
Okay.
So you break ground, right? And within 6 months, the entire project is completely derailed.
Like completely off the rails.
Exactly. The concrete pours are out of sequence. The functional teams are literally screaming at each other in the site trailers. The supply chain has completely fractured.
And the financial backers are probably threatening to pull the plug.
Oh, absolutely. They're breathing down your neck. And here's the kicker, right? You didn't fail at engineering the building.
No, the math was fine.
Right. You failed at engineering the chaos around the building.
Yeah.
So today we are taking an exhaustive surgical look into the anatomy of how massive projects are actually born, executed, and saved from the brink of disaster.
It is so needed.
We've got this immense stack of advanced project management texts, case studies, enterprise architecture research. And the mission today is to distill all of this down and turn you, the listener, into a master architect of execution.
What's fascinating here is that the friction you just described, that catastrophic failure 6 months in, almost never happens because someone, forgot how to calculate a load-bearing tolerance.
Right, it's rarely the physics.
Exactly.
Yeah.
It happens because project management, especially at the absolute highest levels, is this seemingly impossible contradiction.
How do you mean?
Well, you are taking the rigorous, completely deterministic mathematical reality of engineering, right?
Well.
And you are forcing it to operate inside the unpredictable, entirely irrational, and politically charged reality of human behavior.
Oh, wow.
You are basically trying to build a perfectly closed mathematical system inside a completely open, breathing, bleeding human organization.
That contradiction right there, that is exactly what we are going to dissect today. Because the ultimate goal of this deep dive, it isn't to teach you how to avoid that chaos.
You can't avoid it.
Right. If you are doing anything worth doing, the chaos is guaranteed. So the goal is to learn how to engineer a system that actually thrives within it.
Yeah, one that uses that friction for momentum.
Exactly, and delivers the hardware anyway. But to do that, before you even open a scheduling software, before you allocate a single unit of resource or, cut a single piece of steel.
You have to look at the soil you are building on.
Yes. You have to look at the host organization, because if the organizational soil is toxic to your specific type of project, it just doesn't matter how good your blueprints are.
A staggering number of technically brilliant professionals miss this entirely, by the way.
Really? Just complete blind spot.
Oh, absolutely. They assume their job begins the moment the executive board signs the budget approval.
It's like, I have the funding, let's go build.
Exactly.
Yeah.
But the enterprise architecture literature, especially research focused on heavy industry and new product innovation, it reveals a very different reality.
Which is?
Most projects that fail were actually dead on arrival.
Dead on arrival.
Yeah, they fail because they are fundamentally misaligned with the wider organization's operational metabolism right out of the gate.
Operational metabolism. Okay, let's unpack this because the texts provide a phenomenal framework for diagnosing this.
They do.
They point to a specific typology that classifies organizations into 3 distinct bodies when it comes to handling projects.
The Wheelwright and Clark typology.
Yes. And if you are sitting there listening to this, you need to mentally map your current company to one of these 3 profiles. So the first profile is what they call a project-based organization.
Right. And in a purely project-based organization, the entire corporate anatomy is evolved specifically to sustain temporary massive endeavors.
Give me an example of that.
Think of a global civil engineering conglomerate that specializes in building offshore wind farms.
Okay, so massive scale.
Massive. And they don't have a static assembly line churning out the exact same consumer good every single day, right? Their entire existence is moving from one massive bespoke client contract to the next.
So the project is the core business.
Exactly.
Mm-hmm.
Therefore, their centralized operations, their legal departments, their procurement protocols, human resources, all of it is completely attuned to the life cycle of a project.
Right.
They understand how to spin up a team of 300 specialists, deploy them to the North Sea for 2 years, and then completely dismantle that team and reallocate them when the wind farm goes online.
So if you are an engineer inside that kind of machine, you are surrounded by people who speak your language. The project is just the absolute center of the
A
universe.
very comfortable place for a project manager to be.
But that is vastly different from the second profile, which is the project-led organization. How does the metabolism change there?
Well, a project-led organization has a massive, steady-state core operation, but it relies on a dense portfolio of projects to survive and adapt.
Okay, like what?
An automotive manufacturer is the classic example here. The beating heart of the company is the assembly line.
Right, stamping out cars.
Yeah, that line must run 24 hours a day, stamping out identical vehicles. That is a permanent operation. But to keep that line profitable, the company is constantly running parallel projects.
Ah, I
So
see.
they have an R&D project designing the aerodynamic chassis for a vehicle that won't launch for 5 years.
Okay.
They have an internal process improvement project upgrading the welding robotics on the active line.
So the operations run the company today?
Yes, but the projects guarantee the company exists tomorrow. The operations support the projects, and the projects feed the operations.
So there is a symbiotic relationship, but I imagine also a constant tension over resources.
Oh, massive tension.
Because the guy running the assembly line wants all the budget to hit his daily quota, right? But the project manager needs that budget to build the car of the future.
Exactly. It's a constant tug of war.
And that tension gets even more extreme in the third profile, the core operations-led organization.
Yeah, in a core operations-led company, projects are almost an afterthought, or honestly, at best, a necessary evil.
Wow, a necessary evil, like an oil refinery.
Perfect example. Imagine a highly optimized, continuous flow chemical refinery. The entire goal of that facility is to never, ever stop.
Right, downtime is death.
Exactly. They want zero variance, zero disruption, total steady-state efficiency. If you introduce a project into that environment, say you need to shut down a pipeline for 3 weeks to install a new sensor array, you are actively disrupting the core mission of the company,
You are the enemy.
basically.
Mm-hmm.
Projects in this environment exist solely to support the existing operations. They are strictly internal, heavily constrained, and top executive leadership usually wants to hear as little about them as possible once the initial capital expenditure is approved.
Okay, this brings me to an analogy that I think perfectly captures the friction here. I look at a new project like a complex organ transplant.
I like that.
The project is a new heart or a new liver being dropped into a host body. If that host body, the organization, doesn't have the right blood type, the corporate antibodies are going to attack it.
That is exactly what happens.
Right. If you try to run a highly agile, highly disruptive software implementation project inside that conservative, core operations-led chemical refinery, the host body will reject the organ.
It will.
The operations managers will refuse to give you their personnel. The accounting department will block your unconventional procurement requests, and the project just dies on the table.
Yep.
But let me challenge that premise for a second.
Okay.
If I'm hired as the project manager, isn't it my explicit job to fight those antibodies? Aren't I supposed to be the bulldozer that breaks through the organizational resistance and forces the transplant to take, regardless of the host body's metabolism?
That is the myth of the heroic project manager.
The myth.
Yes, and it is responsible for billions of units of wasted capital every year.
Mm-hmm.
You cannot fight the host body and win over a multi-year timeline.
You just get worn down.
Exactly. If you attempt to force a project against the fundamental grain of the organizational environment, you might win a few early battles through sheer force of will, but you will eventually exhaust your political capital.
Right.
You'll burn out your engineering team, and the project will be starved of resources. The environment absolutely dictates the necessary management style.
So what's the alternative? Do you just quit?
No, but if you discover that your project does not fit the host organization, the solution is not to just push harder. The solution is to either fundamentally redesign the parameters of the project so it is recognized as friendly tissue.
Adjust the project to fit the body.
Yes. Or you have to undertake the massive task of changing the organization's strategic alignment before you even launch the project.
Which is a whole other beast. And that concept of strategic alignment is something the sources dig into heavily, specifically referencing Michael Porter's theory of strategic fit.
Yes, Porter's fit.
It's not enough for a project to just be a good idea or technologically sound, right? It has to mechanically lock into the overarching strategy of the company across 3 distinct levels.
Porter's framework is brilliant because it forces you to look at the project as a gear inside a much larger transmission.
Right.
The first level is simply first-order fit, which is basic consistency. Does the stated goal of this project logically align with the stated corporate strategy?
Makes sense.
If your manufacturing company's entire market dominance is built on being the absolute lowest cost provider of bare bones industrial fasteners.
Right, cheap and cheerful.
Yeah, and an engineering team pitches a massive project to develop an ultra-premium titanium alloy fastener with a complex supply chain that fails the first order fit.
Because it contradicts the brand and the manufacturing strategy.
Oh, exactly.
It's a beautifully engineered gear, but it has the wrong teeth for the transmission.
I love that. Exactly. Now, if you pass that, you look for second order fit. This is where activities reinforce each other.
Okay, so it's not just consistent, it's actually helpful.
Right. Does executing this project actually make your other operations better, faster, or more efficient?
Give me an example of that.
Well, going back to that low-cost fastener company, if they implement a project to automate their raw material sorting, that perfectly reinforces their strategy of driving down costs.
Got it. It compounds the advantage.
Yes. And the ultimate level is third-order fit, which is the optimization of effort across all activities. This is where the organization is so seamlessly aligned that information exchange, resource allocation, and product design are all happening with zero wasted effort.
That's the holy grail.
It is. A proposed project has to be evaluated against these three levels of strategic fit before anyone even looks at a technical schematic.
But to really guarantee that fit, you can't just look inward at the company's strategy, right? You have to look outward at the reality of the world the project is going to be born into.
The macro environment.
Exactly. The texts provide a comprehensive environmental assessment model. It's an incredibly practical walkthrough of the external conditions you have to map out.
Like a pestle analysis.
Yeah. Let's build a hypothetical scenario here to walk through this. Let's say we are a project-based engineering firm, and we've just been contracted to build a massive next-generation offshore wind farm near a developing coastal region.
Okay, big project.
Walk me through how we assess the environment before we accept the contract. We start with the political environment.
The political environment dictates the fundamental viability of the terrain. For a massive infrastructure project, like an offshore wind farm, you aren't just dealing with the physics of the ocean, right?
No.
You are dealing with the volatility of the capital city. What is the stability of the current administration? Are they subsidizing renewable energy, or are they heavily lobbied by the fossil fuel industry?
Right. Who holds the power?
And if the administration changes halfway through your 5-year build schedule, will your permits be revoked? You have to engineer a risk mitigation strategy for the political climate just as rigorously as you engineer the corrosion resistance of your turbines.
Next is the social environment. I think engineers often overlook this because it feels unquantifiable, but it can stop a project instantly.
Oh, absolutely. If you are building that wind farm, what is the social impact on the local fishing communities? Are you disrupting their traditional grounds?
That will cause a massive backlash.
You will. And what are the local labor expectations? If you plan to import 1,000 specialized technicians, rather than training the local workforce, you might face massive social unrest, protests, and blockades at your staging areas.
So the social fabric of the environment is a physical constraint on your project.
Very much so.
Then we have the economic environment. This isn't just about the initial funding, is it? It's about macroeconomic stability.
Correct. You have to forecast the economic reality of the host country over the lifespan of the project. What is the inflation rate for the raw materials you need to procure locally?
That could bankrupt the project.
Exactly. If the local currency collapses, can the regional government still afford to purchase the power your wind farm generates? If the economic environment cannot sustain the final product, the project is a failure, even if the engineering is perfect.
Which brings us to the technological environment. Are we bringing state-of-the-art tech into an environment that can't support it?
Right. If your wind turbines require highly specialized proprietary diagnostic software to maintain, does the local grid have the digital infrastructure to support that?
Good question.
Are there local technicians capable of being trained on that technology? Or will you have to fly someone in from across the globe every time a sensor trips? You have to assess the technological maturity of the environment you are operating within.
The next assessment is legal. This is the one that really dictates the physical boundaries of what we can build.
Legal constraints are hard boundaries. What are the environmental impact laws regarding pile driving into the seabed? What are the maritime shipping lane regulations?
You can't just ignore those.
No. And what are the labor laws regarding maximum consecutive working hours for your specialized crane operators? Ignorance of the legal environment will result in injunctions that freeze your project for years.
And finally, the competitive environment. Even for a giant infrastructure project, you have to look at what the rivals are doing.
Definitely. If a competing firm is simultaneously building a massive solar array just inland from your wind farm, how does that impact the regional demand for your power?
It changes the whole ROI calculation.
And more immediately, how does it impact your access to raw materials and heavy lifting equipment in that specific region? Are you going to be in a bidding war for the only 3 heavy lift offshore vessels available in that hemisphere?
When you lay all of that out, the organizational metabolism you belong to, the strategic fit of the project, and that exhaustive assessment of the political, social, economic, technological, legal, and competitive environments, you finally have a true map of the terrain.
Yes.
Only then can you actually start designing the operational boundaries of the project itself, which is the perfect transition into the architecture of the project. We are zooming in from the macro environment down to the specific, invisible walls we are going to build around our engineering team.
This is where the structural design of the project takes shape.
Right.
The research, notably the work by Lampel and Jaha on project orientation, argues that every project must be consciously configured along 3 critical dimensions: project scoping, project programming, and project autonomy.
Let's really pull these dimensions apart, because getting this configuration wrong is like trying to use a sledgehammer to drive a screw.
It is.
Let's start with project scoping. This isn't just a simple document, right? It is a spectrum of certainty.
Right.
On the far left of the spectrum, you have extremely tight, rigid scoping. On the far right, you have incredibly loose, organic scoping. Walk us through the mechanics of tight scoping.
Tight scoping means you are attempting to eliminate all ambiguity before a single physical action is taken. You are fully mapping every single detail up front.
So no surprises allowed.
None. You define the exact tensile strength of the materials, the precise dimensions of every component, the exact sequence of assembly, and the final, unalterable deliverable.
That sounds like it takes a massive amount of planning.
It requires a massive upfront investment in planning and simulation. By locking the scope down completely, you curtail exploration. You're telling the team, do not invent anything new. Simply execute this blueprint to the millimeter.
That sounds incredibly restrictive, but obviously necessary in many fields. Contrast that with the mechanics of loose scoping.
Loose scoping is utilized when you fundamentally do not know what the final deliverable will look like. It is essentially an educated sketch.
An educated sketch.
Yeah. The overarching objective, perhaps you need to design a material that can withstand extreme atmospheric re-entry temperatures, but you leave massive amounts of the technical pathway completely undefined.
You just let them figure it out.
You allow the details, the materials, and even the intermediate goals to emerge organically as the team conducts experiments, fails, learns, and pivots.
Okay, the second dimension is project programming. This deals with the timeline and the milestones. Again, a spectrum from tight to loose. Tight programming is the classic, rigid Gantt chart, right?
Precisely. Tight programming breaks the work into discrete, micromanaged, highly controlled steps. You have strict budgets allocated to specific weeks, mandatory gated check-ins, and very strong incentives tied to compliance.
Sounds like standard corporate project management.
It attempts to foresee every contingency and build a schedule that runs like a metronome. Loose programming, however, removes the gated check-ins. It relies on highly flexible schedules and ties incentives to the achievement of broad, generalized targets rather than daily metric compliance.
The third dimension is project autonomy. How much of an isolated bubble does the team get to work inside? A project with low autonomy is essentially tethered to the broader organization.
Right.
They have to constantly report to higher management, they must justify their daily spend, and they are highly susceptible to external executives dropping in and requesting changes.
High autonomy is the complete opposite. The team is severed from the daily bureaucracy of the host organization.
Like a completely separate unit.
They are given a broad mandate, a block of funding, and immense latitude to move forward independently. They do not report their daily activities, and they aggressively defend their boundaries against outside interference.
So what does this all mean? Let's take these 3 dimensions, scoping, programming, and autonomy, and apply them to the real world.
Sure.
Let's look at the absolute extremes of mechanical and aerospace engineering to see how these profiles look in practice. Take something like the original Lockheed Skunk Works, designing the SR-71 Blackbird in total secrecy. How does that map out?
That is the quintessential example of an exploratory deep tech R&D project. To achieve a breakthrough of that magnitude, inventing an aircraft that flies at Mach 3 at the edge of space, You require a very specific architecture.
And what does that look like on our spectrums?
It requires incredibly loose scoping because the metallurgy and the aerodynamics required literally didn't exist yet, right? The team had to invent the titanium machining processes as they went.
They couldn't scope it because they didn't know how to do it yet.
Exactly. It also required loose programming because you cannot put a strict milestone on a metallurgical breakthrough. If the titanium shatters during a test, you can't just look at a Gantt chart and say, well, the chart says we must start assembly tomorrow.
You have to pivot.
You have to pivot. And crucially, it required maximum absolute autonomy. Kelly Johnson, the leader of Skunk Works, famously demanded total isolation from the Pentagon bureaucracy and Lockheed's own corporate management.
He just locked the door.
He needed a frictionless bubble to operate inside, free from constant progress reports that would have crushed their momentum.
That makes perfect sense for bleeding-edge innovation. But let's swing the pendulum to the exact opposite extreme. Let's look at the engineering of a massive, multi-billion-unit suspension bridge connecting two major metropolitan cities.
Right. Very different beast.
Yeah.
If you attempt to use the Skunk Works architecture on a suspension bridge, people will die, and you will end up in prison.
Yeah, you don't want loose scoping on a bridge.
A bridge requires the absolute tightest scoping humanly possible. You must know the exact geological load-bearing capacity of the bedrock before you start. You cannot pivot and change the gauge of the suspension cables halfway through the build because you had a creative realization.
No improvising.
It requires relentlessly tight programming. The logistics of pouring thousands of tons of concrete in a marine environment mean your schedule is dictated by the chemical curing times of the cement and the tidal patterns of the ocean. Every minute of every day is heavily gated.
And autonomy?
Near zero autonomy. You are building with public funds over navigable waterways, so you have city planners, environmental protection agencies, maritime authorities, and political oversight committees constantly demanding reports and injecting constraints into your daily operations.
I love that contrast. It proves that there is no one right way to structure a project. There's only the right way for the specific environment and objective. But I want to push back on the innovation side for a minute.
Go for it.
When you describe loose programming for an R&D project, I can easily hear a skeptical executive saying, loose programming is just an excuse for engineers who don't want to commit to a hard deadline. It's corporate speak for being sloppy with the budget.
Oh, I've heard that so many times.
Right. How do you defend loose programming as a legitimate engineering management tool?
This raises an important question because that executive reaction is incredibly common, and it stems from a fundamental misunderstanding of uncertainty.
How so?
Traditional managers view anything other than a rigid, date-specific schedule as a lack of discipline. But loose programming is not sloppiness. It is a highly deliberate, disciplined strategy designed specifically for environments characterized by total uncertainty.
Okay, go on.
In an environment where the foundational physics or the material science is unproven, a rigid schedule is actually a hallucination. It is a lie that management tells itself to feel like they are in control.
Wow.
If you mandate a strict timeline on an impossible invention, the engineers will simply hide their failures, falsify their progress reports, and deliver a compromised product just to hit the arbitrary date.
Because they have to feed the Gantt chart.
Yes. Loose programming requires immense discipline because it says, we acknowledge we do not know enough yet to lock in a date, so we will aggressively manage by broad directional targets, rapidly iterating until the uncertainty decreases enough to build a real schedule. It requires far more trust and maturity than simply obeying a Gantt chart.
A rigid schedule in total uncertainty is a hallucination. That is brilliant. You are just writing fiction with dates attached.
Exactly.
Okay, so we have assessed the organizational soil and we have built the architectural boundaries. Our scoping, programming, and autonomy are set. Now, the team is moving. The metal is being cut. The concrete is being poured. The project is alive.
And breathing.
And the second it comes alive, it tries to deviate from the plan. We need a navigation system to keep this massive machine on course. This leads us directly into the mechanics of execution and project control.
This phase is what the vast majority of people visualize when they hear the term project management. It is the delivery-focused, highly analytical reality of execution control. In the literature, this is often referred to as managing the baseline mantra.
The baseline mantra being on time, in budget, to scope.
Exactly. That is the holy trinity of technical project control. During the planning phase, you establish a baseline plan for the schedule, a baseline for the resource cost, and a baseline for the technical deliverables.
The theory.
Yes, your entire job during execution is to constantly measure your actual reality against that theoretical baseline, identify the variances, and take mechanical corrective action to force the project back onto the line.
To navigate that successfully, the texts draw a very sharp line between two concepts that are constantly disastrously confused in corporate environments: KPIs and CSFs. Let's untangle these, starting with KPIs, or key performance indicators.
Key performance indicators are the actual quantifiable metrics used to measure your progress toward your objectives. They are the hard data points.
So the numbers on a spreadsheet.
Yes. A KPI might be the percentage of schedule adherence, the return on investment ratio, or the number of structural defects per 1,000 units. They must be strictly measurable, completely objective, and they must be defined before the execution begins so you have a stable yardstick.
So KPIs are the readouts, but CSF's critical success factors are completely different.
Yes, very different. Critical success factors are the vital underlying areas where the project manager and the leadership team must concentrate their active attention and energy to actually cause the project to succeed.
So it's not a metric, it's an area of focus.
Right. Prominent studies in the field, such as the work by Morris and Huff or Pinto and Slevin, isolated several generic CSFs that apply across industries. These include securing unshakable top management support, maintaining a crystal clear project definition that everyone understands, and ensuring you have adequate human resources and technical talent.
I think the best way to conceptualize the difference between KPIs and CSFs is to look at aviation. Or wait, let's look at maritime navigation, specifically dead reckoning.
Oh, I like nautical analogies.
Right. If you are captaining a massive cargo ship across the ocean, your KPIs are the numbers on your GPS screen. They tell you your current coordinates, your speed over ground, and your estimated time of arrival.
Pure data.
Right. They are pure historical measurements of what is currently happening. But your CSFs, your critical success factors, are the condition of your massive diesel engines, the physical integrity of your hull, the discipline of your crew, and your understanding of the incoming weather system.
Right, the things that actually matter.
The CSFs are the physical realities that actually cause the success of the voyage. The KPIs just measure the result. You cannot manage a ship by staring at the GPS screen and yelling at it to go faster.
No, you definitely cannot.
You manage the ship by maintaining the engines and steering the rudder, the CSFs, so that the GPS screen, the KPIs, eventually reads the numbers you want.
That is a phenomenal mechanical analogy. Far too many project managers spend their entire week staring at the KPIs, massaging the data in spreadsheets, and completely ignoring the CSFs.
Just hoping the numbers change.
They are staring at the GPS while the engine room is flooding. And the most powerful, intricate, and unforgiving tool we have for generating those execution KPIs, particularly regarding time and resource consumption, is earned value analysis, or EVA.
All right, this is what we need to roll up our sleeves and look at the actual mathematics of control. We are going to walk through an earned value analysis masterclass right now.
Let's do it.
And we are going to do it conceptually, focusing on units of value and resource ratios so you understand the physical mechanics of the math without getting lost in specific currencies.
Earned value analysis is vital because traditional accounting is useless for project management.
Why is that?
Traditional accounting just tells you how much resource you have burned. If you have a budget of 100 units and you have burned 50 units, traditional accounting says you are halfway done.
But that's not true.
Exactly, because that doesn't tell you if you actually built anything.
Oh.
You could have burned 50 units of resource and produced absolutely zero usable product. EVA solves this by integrating scope, schedule, and cost into one cohesive mathematical picture.
Let's build a tangible scenario. Let's say our engineering firm has a contract to manufacture 10 highly specialized cooling turbines for a nuclear facility.
Okay, 10 turbines.
We have exactly 10 weeks to build them, and our total budget is 100 units of resource. That means, perfectly averaged out, we should build 1 turbine per week at the cost of 10 units of resource per turbine.
Very clean numbers.
Let's fast forward to the end of week 5. We need to look at the 3 foundational metrics of EVA to see where we stand. The first metric is BCWS.
BCWS stands for Budgeted Cost of Work Scheduled. This metric represents your theoretical plan. Based on your original schedule, how much value were you supposed to have created by this exact moment in time?
It's week 5.
Right. In your scenario, it is the end of week 5. The plan says you should have completed 5 turbines. Since each turbine is worth 10 units of value, your BCWS, your plan value, is 50.
Okay, BCWS is 50. That is the baseline. The second metric is BCWP, which is budgeted cost of work performed. This is the heart of the system. This is the earned value.
Exactly. BCWP strips away the theory and looks at the physical reality on the factory floor. You walk down to the assembly line at the end of week 5 and you count the completed functional turbines.
The actual physical objects.
Yes. Let's say the team encounters severe machining issues and they have only fully completed 4 turbines. Regardless of what the plan said, your actual earned value is based on what you physically produced. 4 turbines at 10 units of value each means your BCWP is 40. You plan to earn 50, but you only earn 40. You are physically behind schedule.
The third metric connects the physical progress to the resource burn rate. This is ACWP, actual cost of work performed.
ACWP looks at the accounting ledger. It asks, what did it actually cost us in real resources to build those 4 completed turbines?
So, the reality of the burn?
Yes. Perhaps the team had to work massive overtime to overcome those machining issues, and they had to air freight replacement parts overnight. You tally up the resources consumed, and you find it actually cost 60 units of resource to build those 4 turbines. So your ACWP is 60.
Let's recap the board at the end of week 5. We have the plan, BCWS, sitting at 50. We have the physical reality, the earned value, BCWP, sitting at 40. And we have the resource burn, ACWP, sitting at 60.
Right.
From those 3 raw numbers, we can calculate the 2 vital indices that act as the pulse of the project. First, the cost performance index, or CPI. How do we calculate that?
The mathematical equation for the cost performance index is BCWP divided by ACWP. It is the earned value divided by the actual cost. It is a pure efficiency ratio.
Okay, run the numbers for us.
In our turbine scenario, you earned 40 units of value, but it cost you 60 units of resource. 40 divided by 60 gives you a CPI of 0.66.
And the universal rule of EVA is that an index of 1.0 is perfect equilibrium. Anything less than 1 means you are bleeding.
Correct. A CPI of 0.66 is catastrophic. It means that for every single unit of resource you inject into the project, you are only generating 0.66 units of physical value. You are operating at a massive deficit.
Wow.
If your CPI is above 1.0, say 1.2, it means you are highly efficient, generating 20% more value than the resources you are consuming. But at 0.66, the project is hemorrhaging.
The second index measures our pace. This is the Scheduled Performance Index, or SPI.
The equation for SPI is BCWP divided by BCWS, earned value divided by the planned schedule value.
So actual versus plan.
We take our 4 completed turbines, representing an earned value of 40, and divide it by our planned value of 50. 40 divided by 50 gives us an SPI of 0.80.
Again, less than 1. We are failing.
An SPI of 0.80 means that you are only accomplishing 80% of the work you originally planned to accomplish in this time frame. You are mathematically losing ground against the clock every single day.
Here's where it gets really interesting. Calculating those indices is incredibly valuable for understanding where you are today. But this is where EVA transcends basic management and becomes a superpower.
Yes.
It isn't just a historical report card telling you how badly you failed last month. It is a mathematical crystal ball. Project managers use these CPI and SPI ratios to accurately predict the future.
That predictive capability is the entire reason EVA was developed, originally by the defense sector for massive aerospace contracts.
How does it predict the future?
Because if you know your CPI is 0.66 at week 5, you can project exactly what your final total cost will be at week 10, assuming your team's efficiency remains constant.
Oh, I see.
You simply take your total original budget, 100 units, and divide it by your CPI of 0.66. The math tells you that if you don't fundamentally change the engineering process or the team dynamics immediately, this project will require over 150 units of resource to complete, destroying your budget.
It just lays the reality out cold.
It removes all the emotional optimism from the project manager who keeps saying, "Don't worry, we'll make up the time next week." The math proves you will not make it up. It forces you to sound the alarm and intervene early.
It is an incredibly beautiful, ruthless, objective system. The numbers do not lie. But, and this is a massive project killing, but you can have the absolute most sophisticated earned value analysis dashboard in the world. Your math can be flawless. But if the procurement manager hates the lead engineer and is deliberately delaying material orders, or if the assembly technicians are exhausted and constantly fighting over tool allocation, the project is going to crash and burn regardless of what your predictive models say.
Absolutely.
Which brings us to the friction point, where the pristine math of engineering slams into the chaotic reality of human nature. This is the ghost in the machine: behavioral and people factors.
This represents the great pivot in project management theory. For decades, the discipline was entirely obsessed with the technical hardware, the PERT charts, the critical path methodologies, the complex EVA algorithms.
Does the math.
Slevin and Pinto's research was revolutionary because it proved that project management is a joint emphasis. A project is a blend of those rigorous technical elements coupled inextricably with behavioral and management concepts. The most brilliant schedule in the world is completely useless if the human beings executing it refuse to cooperate.
Before we dive into the behavioral issues, you just mentioned PERT charts. For the sake of total clarity, let's define that quickly, as it is a foundational piece of that technical hardware.
Certainly. PERT stands for Program Evaluation and Review Technique. It is a highly statistical tool used in project planning to analyze and represent the specific sequence of tasks required to complete a project.
Okay.
It is particularly useful when the duration of individual tasks is highly uncertain. It maps out the dependencies, meaning task B cannot start until task A is finished, and uses statistical probabilities to calculate the absolute minimum time needed to complete the entire project, which we call the critical path. It is a masterpiece of technical scheduling.
But again, PERT is just a map. The people have to drive the route. Slevin and Pinto isolated 12 critical behavioral issues that completely dictate a project manager's actual performance. We can't cover all 12, but we need to do a deep dive into the absolute most vital human failure points. The first one that derails massive engineering efforts is a lack of cross-functional cooperation.
Projects, by their very definition, are cross-functional. You are pulling specialists from deep inside different departmental silos to form a temporary team. You have a structural engineer, a finance auditor, a legal compliance officer, and a marketing director all sitting at the same table.
Sounds like a recipe for a headache.
The problem is, these people have entirely different professional vocabularies, entirely different incentive structures, and fundamentally different worldviews.
Right.
The structural engineer's primary incentive is to build something that will never break, no matter how much it costs. The finance auditor's primary incentive is to cut costs to the absolute bone. The project manager has to somehow bridge these massive functional divides and forge a unified culture.
And that difficulty is multiplied by 1,000 in today's environment of virtual teams. You aren't just dealing with different departments. You are trying to get an orchestra to play a complex symphony when the string section is in Tokyo, the brass section is in Berlin. They have never met face-to-face, and they are communicating entirely through delayed emails and glitchy video calls.
It's so hard.
The friction is immense, which inevitably ignites the next behavioral factor: conflict and negotiations.
Conflict is guaranteed in a project environment because resources are inherently scarce, and the schedule pressure is intense. But the most crucial insight from the behavioral literature is that conflict is not inherently destructive.
Really? People usually try to avoid it.
In fact, if a project team has zero conflict, it usually means they are suffering from groupthink, or they simply do not care enough to argue. Task-based conflict, where the team is passionately debating the best metallurgical composite to use or fiercely negotiating the sequence of an installation, is incredibly healthy. It forces the best technical solution to the surface.
So task conflict is the heat of the forge. It makes the steel stronger, but what destroys the project?
Interpersonal conflict. This is when the debate shifts from your engineering solution is flawed to you are incompetent and I do not respect you.
Yeah. That's toxic.
Once conflict becomes personalized, trust evaporates. Information is hoarded rather than shared, and the cross-functional cooperation we just talked about completely disintegrates. The project manager must be adept at facilitating intense task conflict while aggressively preventing it from deteriorating into interpersonal warfare.
And navigating that requires mastering the third and probably most controversial critical factor: power and politics. I talk to a lot of incredibly talented technical engineers who view politics as a dirty word.
Oh, yes.
They believe that if the math is right and the design is optimal, that should be enough. They despise the idea of having to play political games.
That mindset is the Achilles heel of the brilliant engineer. It is a purely technical worldview, but projects are inherently political entities. They are temporary, disruptive forces competing for permanent, scarce resources.
They need stuff to survive.
You need the best technicians. You need priority access to the manufacturing floor. You need executive budget approval. The manager of the core operations wants those exact same resources for their daily quota. If a project manager refuses to acknowledge the political landscape, if they view building alliances and understanding organizational power dynamics beneath them, their project will simply be starved to death by managers who are better at the political game. You have to secure the power to protect your team.
I have to jump in and play the skeptic here.
Okay, hit me.
We just spent 20 minutes walking through the exquisite mathematical precision of earned value analysis. We have CPI, SPI, predictive forecasting. Why do we treat these soft behavioral skills managing conflict, playing politics, breaking down silos as a separate, almost secondary discipline? Ultimately, isn't it the human beings who are inputting the data, generating the variances, and making the decisions? Why is there such a massive divide between the math and the people in management theory?
That is the most important question of this entire deep dive. To answer it, if we connect this to the bigger picture, we have to look at a fundamental shift in how we understand organizational architecture, dating back to Katz and Kahn in the 1960s.
Okay, Katz and Kahn.
They popularized the concept of open systems. Think of a closed system, like a mechanical watch. You wind the mainspring, you close the case, and the gears turn with absolute predictable precision based entirely on internal physics. It requires nothing from the outside world.
Right.
Early project management theorists treated projects like closed systems. They believed if you just built a perfect PERT chart and calculated your EVA correctly, the project would tick along perfectly.
Just wind up the Gantt chart and walk away.
Exactly. But an organization is not a mechanical watch. It is an open system. It operates much more like a biological organism. You must constantly interact with its environment to survive.
It breathes.
It breathes in raw materials, capital, and human motivation. It processes those inputs through massive internal friction, and it exhales finished products, data, and organizational change. A project is an open system operating inside a larger open system.
So the math we rely on is intimately connected to the biology of the organization.
They are inseparable. The data on your pristine EVA dashboard is not a closed mathematical loop. It is a direct, quantifiable reflection of human behavior.
Oh, wow.
If your engineering team is demoralized because of toxic interpersonal conflict, your actual cost of work perform skyrockets because they're working inefficiently, and your cost performance index collapses.
The math suffers because the people are suffering.
If your stakeholders are fighting a political war over resources, your schedule slips and your schedule performance index plummets. The hard numbers on your dashboard are literally just the exhaust fumes of the soft human interactions happening on the factory floor. If you manage the math but ignore the people, your baseline is a fiction.
The hard numbers are just the exhaust fumes of the human interactions. That is a profound paradigm shift for anyone managing a technical team. If the math is failing, you don't fix the math. You fix the human friction creating the math.
Exactly.
All right, let's fast forward the timeline. The execution is over. The massive offshore wind farm is generating power, or the SR-71 is flying, or the nuclear turbines are installed. Whether the project succeeded brilliantly or failed spectacularly, the organization has a monumental responsibility to harvest the data from that open system and upgrade itself for the next run. This is the final phase. The upgrade, maturity, knowledge transfer, and the postmortem.
This introduces the concept of project management maturity, or PMM. We understand that individual engineers have different levels of competency, from novice to master. But organizations themselves possess a collective maturity level regarding how they handle projects.
How do they measure that?
The major professional bodies, like the Project Management Institute with their PMBOK guide, the Project Management Body of Knowledge, and the Association for Project Management, provide extensive frameworks for companies to audit their own internal sophistication.
And the literature makes the financial case for this very clear. Organizations that invest the capital and the pain required to climb those maturity models achieve a state where their processes are standardized, predictable, and continuously improving.
They save so much money.
These high-maturity companies enjoy significantly lower overall project management costs, drastically fewer schedule overruns, and they simply do not make the same mistake twice. But to climb that maturity ladder requires institutional learning, and this brings up my absolute biggest pet peeve in the corporate engineering world, the lessons learned binder.
Ah, yes, the infamous binder that gathers dust on the shelf until the end of time.
It drives me insane. A massive, grueling 2-year project ends. The team is completely exhausted. Management forces them to sit in a sterile conference room for exactly 1 hour and write down their lessons learned on a whiteboard.
So painful.
An intern types it up into a sterile PDF, saves it to a labyrinthine corporate shared drive, and literally no human being ever looks at it again. A year later, a new project team encounters the exact same supply chain failure, and they have to reinvent the wheel to fix it. It is a staggering tragedy of wasted intellectual capital.
It is entirely too common, and it stems from confusing documentation with actual knowledge transfer. Gathering lessons into a database is easy. Transferring that knowledge into the brains of the next generation of project managers is incredibly difficult.
So how do we fix it?
For lessons to actually alter the organization's maturity, they must be converted into actionable narratives. The literature suggests several highly practical mechanisms to break the curse of the dusty binder and actually inject the knowledge back into the open system.
Let's equip the listeners with these tools right now. How do we build a machine that actually transfers this hard-won knowledge?
The first step is to get the knowledge out of the formal, bureaucratic documentation and inject it into informal, highly social settings.
Social setting.
Human beings are biologically wired to absorb complex information through storytelling, not through bulleted lists in a PDF. Organizations should institute informal, brown bag lunch case studies.
Okay, I like that.
You bring in the project manager of a recently completed, highly difficult project. You buy the engineering department pizza, and you have a completely unvarnished, off-the-record conversation about what actually caught fire, how the political battles were really fought, and how they survived the EVA deficits.
Real talk, basically.
Exactly. When an experienced engineer tells a story about how a specific vendor lied about their material tolerances, the younger engineers remember that narrative forever.
I love that approach. Make it a visceral story, a campfire tale rather than a spreadsheet. What is the formal equivalent to that?
The formal mechanism is building an internal, highly detailed corporate case study library. Instead of a generic list of what went wrong, you commission a comprehensive write-up of the project experience modeled exactly like a Harvard Business School case study.
So it's deep context.
Very deep. You detail the initial macro environment constraints, the fierce cross-functional conflicts, the technical crises, and the specific decisions the leadership team made under pressure. When a newly promoted project manager is assigned a complex build, their first task is to read the historical case studies of similar projects. They must understand the historical context and the inherited technical debt of the organization before they are allowed to draw a new Gantt chart.
But there is a massive behavioral prerequisite for any of this knowledge transfer to actually work. For an engineer or a project manager to sit in that brown bag lunch or write that case study and actually tell the brutal truth about why something failed, there has to be absolute trust. And that relies entirely on the fairness principle in post-project evaluations.
This is the linchpin of organizational learning. If the post-project evaluation process is perceived as fundamentally unfair, punitive, or politically biased by the team being evaluated, they will simply close ranks.
They will just lie.
They will lie, they will hide the data, they will blame external factors, and they will protect themselves. The organization learns absolutely nothing, and the maturity level stagnates.
Let me paint a very specific scenario to illustrate how a lack of fairness destroys a company, because I have seen this exact dynamic play out in the heavy manufacturing sector.
All right, let's hear it.
Imagine an incredibly competent, highly dedicated engineering team inherits what everyone knows is an absolute loser project. It was sold to a major client by an aggressive sales team with completely impossible technical promises and a fictional timeline, long before the engineering team was even assembled.
Oh, this happens all the time.
It is massively under-resourced from day one. Through absolute heroic, superhuman efforts, the team is working 80-hour weeks, inventing brilliant mechanical workarounds on the fly, calling in every personal favor they have with suppliers. They manage to keep the disaster contained. They actually deliver a functional product, albeit predictably late and over the fictional budget. If the organization's executive leadership uses a blind, rigid KPI evaluation system that simply looks at the final SPI and CPI numbers, punishes the team for missing the original baseline, and cuts their performance bonuses, what happens to that open system?
You completely and irreversibly demoralize your absolute best problem solvers.
Yeah.
They feel a deep, justified anger at the complete unfairness of the verdict. They know they performed a miracle, and they were punished for it.
And what does that do to the company?
The secondary consequence is even worse for the organization. The official takeaway from the evaluation becomes, this engineering team failed to execute the baseline schedule. The massive systemic flaw that the sales department is allowed to commit the company to mathematically impossible contracts without engineering oversight is completely ignored.
Wow.
The data feeding the organizational maturity model is poisoned. You punish the heroes, you protect the systemic rot, and you guarantee the exact same failure will happen on the next contract.
Exactly. If the evaluation isn't fiercely contextualized, if it doesn't look at the project as a chaotic open system reacting to impossible inputs, you are just weaponizing the math against your own people.
Which brings everything full circle. You cannot evaluate a project in a mathematical vacuum, relying solely on the final earned value readouts. You must evaluate the project within the full context of its original organizational fit, the rigidity of its architectural scoping, and the intense behavioral and political constraints the team was forced to overcome.
We have covered incredible foundational ground today. We started at the macro level, mapping the organizational metabolism and the strategic terrain. We zoomed in to construct the invisible architecture of scoping, programming, and autonomy.
Right.
We walked through the unforgiving predictive mathematics of earned value control, pivoted into the messy political reality of behavioral psychology, and finished by outlining how to actually extract truth and maturity from the ashes of a completed project.
It is a massive, highly interconnected life cycle. Understanding how the rigid engineering mathematics interact with the fluid human dynamics is the fundamental difference between someone who just administrates a schedule and a true architect of execution.
I want to pull all of these threads together and leave you, the listener, with a final, highly provocative thought to mull over as you head back to your own projects.
Okay.
We spent this session balancing the rigid control systems, the tight programming, the EVA math, the critical path algorithms against the behavioral human elements of conflict, politics, and motivation. Looking forward into the very near future, artificial intelligence and machine learning algorithms are becoming exponentially more sophisticated.
Yes, they are.
Within a few years, AI will be exceptionally, flawlessly good at the control aspect. And AI will be able to instantly calculate earned value across 10,000 variables, optimize massive global supply chain schedules in real time, and track 1,000 KPIs simultaneously without ever making a mathematical error.
Oh, without a doubt.
If the machine eventually handles all the rigorous math and scheduling perfectly, will the future of project management become almost entirely behavioral? Will the master project manager of tomorrow be less of a technical engineer staring at a Gantt chart and almost entirely an organizational psychologist dedicated to managing human friction, translating complex narratives, and ensuring political alignment in an open system?
It is a profound and imminent shift. The technical baseline will almost certainly be automated, but managing the chaos of the open system, the irrational, brilliant, unpredictable human beings, will remain a deeply, uniquely human discipline.
Victory belongs to those who refuse to lose. Thanks for riding with me, Design Junkies. Stay hungry. If this episode gave you even one solid takeaway, drop a comment. It takes you a few seconds, but it tells me this workbench is actually helping and worth keeping alive. We don't make a dime off this, and that's by design. As long as it's helping you get sharper, that's enough.